Hello everyone, and thank you for joining us for today's Surface Measurement Systems webinar, organized in collaboration with Aston University and Heriott University, with a special thanks to Dr. Ahmed Rezek and Dr. Minjat van der Spek for joining us today. The title of today's overall session is Understanding Materials Sorption Properties to Address Global Issues. Now, before we go on, I'd just like to highlight that unfortunately one of our speakers has had a slight change in schedule, so we'll be presenting later than expected, but he will still be here, so please do not be concerned. Before we get into the presentations proper, I just wanted to highlight that each session will be accompanied by a live Q&A session. So you'll be able to submit questions in the questions tab if you want to submit them in writing, and then I will put your question to the speaker at the end of their presentation. Or if you have maybe a slightly longer, a complicated, or a two-part question that you would like to discuss directly with the speaker, you can raise your hand and we'll let you know when you can unmute your microphone to ask your question. So first off, we're just going to have a quick presentation from Nectaria Servi, the European Sales Manager for Surface Measurement Systems, who is going to take us quickly through SMS, the instruments we produce, and the general techniques that have been employed in the studies here, so that you have a good grounding of understanding for how the science here was conducted in the following presentation. So without further ado, I will now hand over to Nectaria.
Good morning, everyone, and thank you for attending our workshop today. And I have to say that this is one of the hottest topics of the year. I will start with a few slides and I will present the company. For those that they don't know Surface Measurement Systems, it was incorporated in 1990, and the founder was Professor Daryl Williams, who is still a professor at Imperial College Chemical Engineering Department, and he's our managing director. The company started with one person, Daryl, and at the moment we have 5 subsidiaries and 2 manufacturing facilities and over 100 staff worldwide. Surface Measurement Systems LLC, what we're doing, we are manufacturing systems for the unique characterization of solutions for solid state materials. And the first system that we manufactured in 1991, the first TBS, as you can see here on my slide, was delivered to Pfizer in 1992. And at the moment, we do have more than 2,000 units worldwide installed. Surface Measurement Systems Holding, LLC, our headquarters are in Alberton, London, where we have our manufacturing facility, R&D, sales and marketing. Then we do have the same structure at Surface Measurement Systems in Allentown, Pennsylvania. SMS Instruments in India, in Hyderabad. We do have Surface Measurement Systems in Germany with 2 salespeople at the moment and 2 service engineers. And we do have the SMS technology in Shanghai as well. And recently, as you have seen on the social media and on our website, we have launched the PCL, the Particle Characterization Laboratory in India. So in the UK and in the USA, we have, as I mentioned, manufacturing and production. We do have quality control and finance and accounting. And in both sides, we do have marketing and sales, and the same structure in India as well. In the UK, USA, and India, we do have labs. In the UK, we mainly do demonstration, sample analysis, and some contract work. And in India, we're doing purely contract work. And in the USA, again, demonstration, sample analysis, and some contract work as well. And we're also collaborating with academia and institutions for collaborative research work as well. So SMS manufactures three main solutions: the dynamic vapor sorption instruments. We do have a range of DVS instruments that they measure uptake and loss of moisture, organic vapors, and or gases by a sample, allowing sorption behavior to be accurately determined, as you can see here on a small graph. Then we have the surface energy analyzer, as we call it, IGC-SEA. Our SEA is unique and allows characterization of surface and bulk properties of powders, particulates, fibers, films, and semi-solids, using a fully automated inverse gas chromatography principle. And it is the first instrument of its kind. And then we have the vapor pressure analyzer, our VPA, allows determination of the vapor pressure of various ionic liquids and solids under different temperature conditions. This instrument is based on the Knudsen fusion cell method, which is adopted in the OECD regulations. And this is our DVS products. As you can see here, the DVS Intrinsic Plus, the DVS Adventure, DVS Resolution, DVS Discovery, where you can analyze two samples under the same conditions, the DVS Carbon, one of our newest systems for CO2 and water measurements, the DVS Endeavor, where you can analyze 5 samples under the same conditions, and the DVS Vacuum, more porous materials. So the systems, I'm not going to go to detail. All the systems, they have differences in temperature, in their different capabilities, and you can analyze various materials. So the PCL, the Particle Characterization Laboratory in India, is a new part of our business. It is based in Hyderabad in India, where we do sample analysis, not only DVS and IGC-SEA, but there are different systems, as you can see here, that we're using for the pharmaceutical industry. So that's all for me. If you need more information about our systems and our contract lab, please email us, or we can discuss after the presentations. At the moment, we do have 4 presentations, and I will pass it on to Dr. Mindert van der Spek, who is a lecturer at the University of Heriott up in Edinburgh. And his presentation, CO2 water, CO2 co-adsorption measurements on amine functionalized polymer resin adsorbents. Thank you, Mindert.
Okay, well, now I can't see my own. Yeah, there we go. Well, thank you, Nectaria, for having me today, and it's a pleasure to be with SMS and to do a webinar again, or take part in one of your webinars again. So we've been working with the DVS vacuum for the last 3.5, 4 years, and have done quite some successful research with that. So I will indeed be presenting co-adsorption and pure component isotherm measurements on direct air capture adsorbents using the DVS vacuum. I'm just trying to see how I can, like this, I think I can remove all that. Okay, good. Now you can actually see my screen. And this work, of course, wasn't done by myself, so there are contributions from John Young, Enrique Garcia Diaz, Katia Piscina, Susana Garcia, and myself. And we are at the Research Center for Carbon Solutions at Heriott University. So first, a little bit of context. So what is it that we are doing? So we look at direct air capture of CO2. So we try to suck CO2 out of the air with amine functionalized adsorbents. And the reason why we like amine functionalized adsorbents is because they really bind CO2 very well, very strongly, and especially in what we call the Henry regime. So the very low partial pressure regime of CO2, and that's basically what we have in the air, right? We have currently a concentration of 420 ppm. Unfortunately, that is rising, and that's also one of the reasons why we study direct air capture. Now, We started off with a very benchmark adsorbent, and we started off with this one because it's a adsorbent that you can just buy commercially. It's called Levatite, VPOC 1065. There are a number of other ones, of course, and it's a polymer resin that originally was developed for wastewater treatment purposes. So it's an anion exchange resin. When I made this presentation, we suspected that the Climeworks Generation 1 sorbent might be very similar to it, very simply because the characteristics of what they list in one of their first patents is similar to Levatite. But I'm not sure if that's the case. It was a hypothesis, but like I said, you can buy this off the shelf with Lanxess, and that makes it a very good sorbent to study as a benchmark. So what we wanted to do initially is gain a very deep understanding of CO2 and water, and also CO2 water co-adsorption on a benchmark amine functionalized sorbent. And the reason for that is that I'll come to that. What we wanted to do with that information or with that understanding is develop sound mathematical descriptions of the effect of water on CO2 adsorption equilibrium, and then understand how these descriptions affect process performance, because what is really, what up to a couple of years was really not very well known, or what the information that wasn't out there in the public domain was, let's say, independent modeling studies of direct air capture machines, direct air capture processes. And in the meantime, some have been published, including our own. But what is still really an issue is that there is very little data on a range of different adsorbents for direct air capture, especially the type of data that you need to input into process models, and that's where we make a contribution. So that is really very important. We need much better descriptions of the fundamentals for modeling purposes, and not only the descriptions, we just basically also need the raw data, and that's where also the DVS vacuum has become very, very useful. Now, I'm just going to jump to a result right away. And what I'm showing here is some modeling that we have done for a direct air capture process. And what you see here is two key performance indicators. So on the horizontal axis, we show the productivity. So basically, how much CO2 can you capture per cubic meter of adsorbent or adsorbent bed per day? And then on the vertical axis, we show the work equivalent. So that's a measure of the amount of energy, but all fed back to second law work that you need to achieve that. And what you see here is 3 Pareto fronts. And they are basically Pareto fronts for CO2 that is captured and that is purified to purity over 95% and optimized for work equivalent productivity. And what you see immediately is that if you don't have a co-adsorption description in your model, and that's what the Pareto front that you see here, then the predicted work equivalent is higher and the predicted productivity is lower than when you do have co-adsorption descriptions. So here immediately you see why it is important to have very good understanding and also mathematical description of water CO2 co-adsorption. Now, one thing on the color bar, so the color bar just shows what is the vacuum pressure in the process that we've used. We've used a minimum of 0.1 bar, so 100 millibar, because that's basically what in industrial settings what you go to. But this is the I will show this slide again later once I've told the whole story. So what have we done? We started off with co-adsorption isotherm model development. So if we're talking adsorption, then one of the most fundamental things are the isotherms, which basically dictate how much CO2 or water or whatever adsorbs onto a solid surface at a given temperature and then at a range of pressures. So what we did is a literature review of potential mechanisms for the co-adsorption of water and CO2. And then we derived a model to describe that. And then we went on to do pure component isotherm measurements with the DVS vacuum, and we fitted isotherm models for that, for water and for CO2. And then we went on to do co-adsorption isotherm measurements also with the DVS vacuum and fitted again CO2 and water. And the reason why we acquired the DVS vacuum is that it, under certain assumptions and in certain conditions, it allows you to do these co-adsorption measurements and to differentiate between how much CO2 and water is absorbed. And then finally, what we did is DAC, direct air capture process modeling. So we modeled cyclic direct air capture processes to understand the performance of these processes and also to see how we could optimize them. Now, I will leave the model derivation for what it is. I have some in the back of slides for who's interested, but it's also published in our 2021 paper in Energy and Environmental Science. But I'll focus on the other elements. So let's look firstly at the binary CO2 water co-adsorption. So if we look at the chemistry, what has been observed, in numerous studies is that under wet conditions, virtually all primary or secondary amine functionalized sorbents have an increased CO2 capture capacity, and especially at 400 ppm, and we will show that later. And we think there are three inhibiting mechanisms for CO2 adsorption under humidity, so in the presence of water. By the way, our thinking has evolved since this presentation. That's basically that's based also on work that we're doing now. So there's probably more going on, but this was the original model that we developed. So we said one of the effects or mechanisms is an inhibiting effect. So if you have an amino group that is grafted or tethered to what kind of solid structure surface you have, then water will simply hydrogen bond to that amino group, right? So you'll get layers of water, and that basically takes away that amino group for the CO2 because it's taken up by water. It's, CO2 will bond much stronger to the amino group, but it will be more difficult to reach it. So there will be some sort of an effect of side blockage there. Then secondly, the theory stated that there will be a change in stoichiometry. So what you see in absolutely dry conditions is that you would form this ion pair, which is basically a carbamate and here an ammonium group. So you have a negatively charged carbamate and here you have a positively charged ammonium group. But under wet conditions, that ammonium group can also combine with a bicarbonate group, which is the HCO3 minus here. So that means that instead of two amino groups, because for carbamate you need an amino group, and for ammonium to form you need an amino group, or that is an amino group, you can bind CO2 with one amino group. So that would imply a change in stoichiometry. And then thirdly, we also know from in operando FTIR studies, for instance, that were published, that it's not only ammonium carbamate and ammonium bicarbonate, but also carbamic acid that is being formed. And that's what you find here. But carbamic acid isn't necessarily stable, so it needs to be stabilized by some other molecule. For instance, by a carbamic acid molecule that is linked to an amino group next to the site where you're absorbing your CO2. But under wet conditions, it can also be stabilized simply by a water molecule. And that has an influence on the heat of adsorption, because the heat of adsorption of the paired carbamic acid is higher than the heat of adsorption when the carbamic acid is stabilized by a water molecule. So now about the DVS vacuum, it allows easy co-adsorption measurements if and only, but if, and that's an assumption that has to be tested first, if water is not displaced by CO2. So that's an important assumption. So what you can do, and I'll show that later, if you know that water will not be displaced by CO2, you need to establish that, for instance, with breakthrough experiments before you do this kind of analysis. But what you can do then is load water onto the sorbent and then in small steps add CO2. So that means that you know how much water has been taken up on the adsorbent, and then you also can measure then with the gravimetric balance how much additional CO2 is taken up. Now, just very quickly on the DVS, you have two gas or vapor flows that flow into the system, here represented in green in the bottom of the graph. Then you have a sample with a sample pan where you have your sorbent sample. You have a reference pan to correct for any buoyancy that might happen. And then you have a microbalance here that measures how that measures the weight of the sample in your pan. Then the pressure is controlled by a butterfly valve, or basically by how much you flow, and by a butterfly valve that is located behind the sample. And then there's a vacuum pump that helps maintain the vacuum that you want. And you can operate this system in the most simplest configuration between 25 and 70 degrees C. So this is what we've done. So what you see here is how you say, a dynamic experiment. So you see on the horizontal axis the time in minutes that the experiment took, and on the vertical axis you see the mass. And what you see is that we started with a mass of just under 25 milligram, and then you see that the mass increased as we introduced gases or vapors to the sample. And this particular experiment was a co-adsorption experiment for at 25 degrees and at 30% relative humidity. So what we did first, and you see that here nicely depicted, is we did water adsorption first. And you see that equilibrium is reached nicely. The curve flattens out nicely, and then in several subsequent steps, we added CO2 to measure how much CO2 is adsorbed at certain partial pressure. So that's the yellow surface here, or the yellow plane. Now I already told you that this approach, this method works if water is not desorbed by the presence of CO2. And that was perfectly fine at a relative humidity of about 60% or lower. But we also saw unexpected behavior when we went to very high relative humidity, so 80% and above. And what you see then is that actually is that actually, oh, I have a drawing tool menu. That's nice. No, I need to go back to that slide. Look at that, I have a spotlight. This is fantastic. Here you see these dents in the graph. And so every time we or at some moments when we added more CO2, so we stepped to a new partial pressure set point of CO2, we see that some gas or vapor was desorbed. And we don't know whether that is water or it was CO2 that was already absorbed. And of course, first we assumed that it would have been water, but then we tried to close the mass balance for CO2 and it didn't work. So there's probably some mixed desorption going on. And that's a difficulty, and that's a challenge that we have now. We're also talking to service measurement systems how we can further develop the DVS to be able to close the mass balance. But that's that's future work. Now what I said already. So water enhances the affinity and probably blocks some sites. And what I'm going to show you is the result of the co-adsorption experiments. And basically what I'm going to show you is an enhancement factor. So an enhancement factor that basically shows what is the CO2 uptake in wet conditions versus the CO2 uptake in dry conditions. So how much does the presence of humidity enhance the CO2 uptake on your adsorbent? And we have here first the results for 25 degrees and for 30% relative humidity and for 55% relative humidity. And here on the horizontal axis, we show the CO2 pressure in bar, and on the vertical axis, we show the enhancement. And an enhancement of 1 means basically that the same amount of CO2 is adsorbed in wet conditions as it is adsorbed in dry conditions. So what you see immediately is that there's a declining trend. So at very low partial pressures, and especially in the Henry regime, you have much more CO2 uptake than in wet conditions than in dry conditions. And that's actually very helpful because, for direct air capture, we have very low CO2 partial pressure. So that means that at ambient conditions, you actually absorb up to double the amount of CO2 in the presence of humidity. So that's fantastic. What you also see is that it completely flattens out and goes to about 1, so no additional uptake at higher partial pressures. And that is actually also beneficial because you have to imagine that when you want to adsorb CO2, you also need to desorb it from your sorbent. And that happens in an environment where you don't have much, or if any, nitrogen or other air components. So your partial pressure of the CO2 will actually be quite a lot higher than the 400 ppm. It will be something around 0.2 or 0.3 bar perhaps, and then you don't have an enhancement. So that's actually beneficial because so the thermodynamics work in our favor in that respect. Now we've done exactly the same for 70 degrees. We also have it for 50 degrees, but the trend is very much the same. And a question that we have is, so you see that the blue line even goes a little bit below the parity point. So no additional uptake in the presence of humidity, and it seems to suggest that there may actually be a little bit less uptake in the presence of humidity, and that may be caused, for instance, by side blocking or by limited access to the amino groups. But this needs to be confirmed on many more materials. So we need much more of this work on a range of different amine functionalized solvents. Now, so what we did is we developed 2 isotherm models. One is mechanistic, so completely follows the mechanisms that I showed earlier, so the chemical, so the chemistry and the side blockage. The other one is a little bit simpler, so it's more empirical. A weighted average dual side TOF model is what we call it, where we assume that the wet and dry sides have 2 distinct isotherms, and we basically with the distribution function, you assign how much of that isotherm is of each isotherm is present, given a certain relative humidity. We also compared it with an empirical model that was available in the literature, and that was the first such model for an amine functionalized group. Also work that I was involved in, and we'll show you the results again. First we come to the isotherms. So we show you here different examples at different temperatures and relative humidities. This one is for 25C and for a relative humidity of 55%. What you see here is the partial pressure again, and here you see the CO2 loading. And this is very simply an isotherm of CO2. And what you see, the red crosses are the experimental results, and then the lines are the different models. So we have in blue the mechanistic model, in dotted orange or dashed orange we have the weighted average dual side TOF model, and then in the green dotted line we have the Stampi-Bombelli et al. Model. And you see it here for different temperatures, different relative humidities, and so I think each model predicts better or worse at a different set point. So we didn't find that one model always outperformed the other models, and they all have their regions where they are okay. But what we did see is that the mechanistic model is just across the range of temperatures and relative humidities is pretty accurate in predicting adsorption. Now the process modeling. This is a very typical direct air capture solid adsorption process. So it consists of 5 steps. First, here on the very right, you start with adsorption. You flow air through an adsorption bed. That can be a monolith structure, or it can be a thin sheet of adsorbent beads or pellets. can also be a film. That's something that people are experimenting with. And the CO2 binds to the adsorbent, and the air continues to flow to the atmosphere. And then we go into regeneration. So we first evacuate the bed to get rid of all the nitrogen and oxygen. Then we heat up the bed, still while having the bed open to the atmosphere to get rid of even more nitrogen and oxygen and water as well. And then we heat further, and we do a desorption step where the CO2 comes out relatively pure, only contaminated with water. But water you can knock out easily in a water trap. And then it can go to storage, or it can go into a greenhouse, or you can use it for power to X or whatever you want to use it for. It achieves over 95% purity, almost always. No, I mean not almost always, but that's the cutoff that we took. We modeled now for ambient conditions of 15 degrees C and 55% relative humidity, and we did 3,000 Monte Carlo simulations for heuristic optimization using each of the isotherm models that we had. And what we varied was vacuum pressure, heating temperature, heating time, desorption time, and the extent of bed saturation during adsorption. So instead of timing the adsorption step, we had a cutoff point for the amount of saturation, which is more, which is actually much more helpful if you're trying to optimize a cycle. Now here are some results already, and what you see here is some violin plots, and they show the distributions of obtained CO2 purity. So this looks only at purity, and it goes from 0 to 100% pure CO2. And the violin plots are for the 4 different options. So in case you don't have any co-adsorption, in case you have use the mechanistic co-adsorption model, in case you use the dual side TOF model, and in case you use the empirical model that we developed a couple of years ago. And what you see already is that there's a massive difference in the purities that you obtain. So you see that a number of models, so for instance, no co-adsorption and the VAS model, the bulk of the data points had purities of 90% or over. You see that the mechanistic model has a bit more of a tail towards lower purities as well. You see that the Stampy model has an even longer tail in purities. And then we come back to this slide that I showed already before. So now you know the whole background of this slide and why it is important. But what you see here is indeed that you can not model or take co-adsorption into account, but then you get very different results than what you would get if you do take co-adsorption into account. So this slide basically shows the importance, and it also shows that the performance of a direct air capture process, when you model it, it's much better than when you do take co-adsorption into account and when you don't. So this is really critical. And I talk quite a bit to people in the direct air capture industry and also in the adsorbent industry, and water CO2 co-adsorption is really the important thing to get much more data on at the moment, because for many adsorbents that's not either. So if anybody is developing adsorbents, by all means also try to report the water adsorption isotherms on your adsorbents, and if you can also measure the water CO2 adsorption. It's we really need it for process design. Now, other interesting observations. Yeah, this is what I just said before. This is again for Lewatit. You see that if we go to higher temperatures for Lewatit, that the hysteresis becomes much smaller. So that would support either a kinetic effect in the and then either what I said before, it might be mass transfer related, so channels closing, or it might be chemical kinetics related, so that you simply have an energy hump that you need to overcome for the desorption. So these materials are really, it's funny because Lewatit is such a simple thing that has been around in the market for years, and we're super excited to try and understand it. So we're working with people at Berkeley to do in situ NMR to try to understand exactly which CO2 and water uptake is happening in wet and in dry conditions, We're working with people at EPFL to do heat of capacity measurements, and all these pieces of the puzzle, they give us super interesting information. Actually, yeah, I had never thought that such a simple off-the-shelf material would be so fascinating, but it is. One other thing that we found is that pure water isotherms, they are a function of relative humidity and temperature. So again, the common knowledge for maybe physical adsorbents is that water uptake is only a function of relative humidity, and the effect of temperature is actually captured through the relative humidity equation. But with our sorbents, we consistently see that that's not the case. So with the amine functional adsorbents, there is actually a temperature effect that you do need to take into account when making the models for your isotherms. So on to some conclusions. I think we are starting to gain a deep understanding of water CO2 interactions, and they are key for DUC process design. So that's really important. You cannot do DUC process design if you solid sorbent DUC process design if you do not understand and measure and model the water CO2 interactions. We know that water affects the affinity through stoichiometry and heat of adsorption. So basically, the CO2 isotherm in wet conditions becomes steeper in the origin in the Henry regime. So it affects the affinity, and that is really important and is really helpful as well for direct air capture. And also perhaps causes side blockage. So that's still a question mark, but we hypothesize that that's the case. So we generated a comprehensive set of co-adsorption data with the devious vacuum as a critical instrument. There aren't many other instruments that mimic that capability. We have provided new co-adsorption isotherm adjustments or models, and they provide a good fit for our experimental data. And we have seen that co-adsorption significantly impacts the performance indicators and optimal operating conditions of a direct air capture process. So again, this is really key to understanding the performance of a real DUC process. I have some backup slides if anybody has questions, but for the moment, I wanted to leave it with this.
Thank you. Thank you, Minder. That was a very interesting presentation. And would it be possible to, after the workshop, to share the presentation with us so we can send it over to the attendees?
Mine is a couple of slides of new work. Yes, that will definitely be possible.
Okay, perfect.
Yeah.
Thank you very much. So any questions, please unmute yourselves. It's good to hear your voice, and yeah, happy to have a discussion.
Mayan Fox, you've been unmuted from our side, so you can ask.
Okay, yeah, so can you hear me?
Yes.
Okay, great. So there's something that I did not understand in the hysteresis graphs. Why is the desorption higher higher in loading? So when we have desorption, the loading is higher at the same pressure. I don't understand why that is the result of hysteresis.
Well, that is in fact hysteresis. So you mean for water, or do you mean for CO2?
I think it was in both.
No, it was in both. I'm just wondering to which slide I should go.
I'll just start rolling back. I'll let you know when I see the one. It was with the Levitt. It was with the commercial material that you were looking at.
No, wait. I think it was later.
Yeah.
I think this is one of them, right?
I can't see the slide.
Oh, okay. Now I'm showing the screen again. Yeah. Sorry, I wasn't the presenter anymore, so I was scrolling my slides, but you weren't seeing it. But now I'm the presenter again. So this is the one, I suppose.
Yeah. This is a good example. So yeah, I understand the basic concept of hysteresis. Like I would expect that there would be, for example, more energy required desorb than you would actually get from the adsorption. But I don't understand how that represents itself here in loading.
Well, it basically, so what the isotherm says is how much CO2 is on the material at a certain pressure, right? So if we look at the partial pressure of 0.4, for instance, what our results say is that if you are in the adsorption mode, hold on, I'll take the spotlight again. If you are in the adsorption mode, then your loading is a little bit lower than when you're in the desorption mode. And first, we did think that potentially that was a result of improper or incomplete equilibration, but we tested and tested and tested again. And every time we saw in the dynamic graphs basically that the uptake was completely flattened out, so that actually the system was equilibrated. Now, what this means is that, for instance, if you adsorb CO2 onto your material and you go all the way up to 1 bar, if you start desorbing, you start reducing the pressure again. But reduction of that pressure only is apparently not sufficient to reach the same loading again as you had at the adsorption branch. So that would imply that there is a barrier somewhere. And that barrier may be in blocked pathways because of channels or pores closing. So that is a very real possibility in this material because it's a polymer resin, and we know that this kind of behavior happens with polymer resins. The alternative explanation is that you indeed need to go over an energy barrier. If you think of an Arrhenius equation, for instance, right, where you also have the energy barrier and an exponent. So you simply need more temperature to add also temperature to be able to release the CO2 again. Okay. I don't know if this fully answers your question, but this is what we think.
That was it. I was explaining that basically when you lower the pressure, the carbon dioxide sticks around, so it doesn't leave. So in that sense, it makes sense to me. Okay, thank you. Thank you.
You're welcome.
Any other questions?
I believe Paul wanted to ask a question.
Hello, can you hear me?
Yes, is that Paul Jacobi?
That's me. Hi, Mike Ninja.
Hey there.
Don't want to steal the spotlight. I know I'm going to talk right after. But I was just curious, have you looked at the surface chemistry of the amines during the desorption process? Is that possible with any techniques? Just to get a little bit more insight about the actual species on the surface while the process occurs.
Yeah, so there is limited information out there. So on primary amine functionalized materials, we found one study who did in operando FTIR. So they looked at the surface chemistry with FTIR, and I mean FTIR can give away quite a lot, but it's also not per se always the most accurate. So what we have been doing with partners at the University of California, Berkeley, is do in operando NMR. And I can tell you that this material, levatite, is a difficult bugger. So it has taken them quite a lot of time and effort to kind of understand what is going on. But in a nutshell, what is confirmed is indeed bicarbonates, carbamates, carbamic acid a little bit. So all the things that we thought were present are present, but their concentrations will differ at different relative humidities.
Is this relaxometry or solid state NMR mass?
I know close to nothing about NMR, so you would have to ask them. But it's kind of the same that was done on the diamine functionalized materials. Of the Jeff Long group, so this is Jeff Reimer's group who's doing that. But there are some papers out there where their methods and techniques are explained. So I would refer you to those.
Thanks. It's a very interesting open question.
Yeah.
Perfect. Thank you, Ming. I think Connor has got a question as well.
Yes, hello. Hi, thanks, Victoria. Yeah, my one question would be, how regenerative are these materials? So upon multiple cycles of water absorption, CO2 absorption, are you getting similar kinetics and capacities upon multiple cycles?
Yeah, they are very regenerative actually, which is maybe a bit of a surprise, and they even tend to perform better in real life than what people had expected after cyclic experiments in the lab. The one problem that you do have is that if you have oxygen and temperature, so a higher temperature at the same time, then the the amino groups will degrade. But you can engineer that out. So I don't know if my screen is still sharing, is it?
It is, yeah.
It is. Okay, that's basically why we do this 5-step cycle that we do, because what we do is we evacuate first, before we start heating, we evacuate first all the nitrogen and oxygen from the bed. So that removes the oxygen as much as we can. Then we start heating and remove a little bit more, because as you start heating, also some of the water starts to desorb. So more oxygen is thereby also released from the pores and from the bed voids. And only then we move to the full regeneration temperature of the sorbent. So you can engineer that degradation effect out, and it actually works quite well.
Okay, fantastic. Thank you very much.
Yeah.
Minja, we have a question here from the audience, and they just ask, could you please give more detail on how to set the method on DVS for the co-adsorption measurement?
Yeah, I mean, let me skip to that slide then, because I think the picture here is actually quite telling, right? So what we do is, of course, you first need to outgas completely, because water and CO2 they adsorb so strongly to any material. Sorry, not to any material, but to this material, any amine functionalized material, that you need to get rid of the water and CO2 as much as you can. So we need, quite proper outgassing. I think we do it overnight at 100 degrees C. So for at least 8 hours. Then you have your baseline here that you see here at, let's say T is 1,000, and then first we load a known amount of water to the sorbent. So we set the relative humidity, and that relative humidity will stay the same throughout the process. Now we have done this in the semi-static mode. So for the ones who know DVS or vacuum or DVS carbon, so we've done this in the semi-static mode. So that means that the gases or the adsorbates aren't flowed over the material continuously, but they're pulsed into the system until a certain set point partial pressure is reached. And then once we have that baseline, so we have the water saturated sorbent sample, then we do a couple of steps of CO2 in injection. So we have again a different amount of or a couple of set points on partial pressure. In this case, we have 1, 2, 3, 4. 1, 2, 3, 4. Yes. So we slowly increase the partial pressure of the CO2, and we let it equilibrate every time. So you see here that equilibrium is nicely reached. Here as well. And then we step on. So it's a relatively straightforward process, but and I think this is really important. The assumption is, and that needs to be tested before, that water is not desorbed, because otherwise you cannot assume that this whole increase in mass that you measure here can be attributed to CO2 adsorption.
Thank you. And then we just have one last question here. What are your regeneration conditions for removing co-absorbed water?
In the models or in the machine, in the Normally the regeneration conditions, so what do we do? If you look at this, let's see if I can go. No, no, my machine is stuck. Sorry. Well, what we do vacuum and kind of heating to 70 degrees to already remove as much water as we can, but that's definitely not enough. So a lot of the water will actually desorb together with the CO2. So we go to 100 degrees C at a vacuum of 0.1, 0.2 bar, more or less, 0.3. So these are the regeneration conditions.
Thank you. I think that's all the questions we have. So thank you so much, Heriott, for being with us here today and sharing your work with us.
It's a pleasure.
Okay. And now we'll pass it on to Polly Akomi. He's our DVS product manager, and his presentation, it's novel applications with DVS Carbon and BTA Frontier, BTA Breakthrough Analyzer.
Okay. Yes, again, good morning, everyone. Thank you for joining us for this seminar. I'm going to continue talking about CO2 capture as a very pertinent problem in our current day and age, and talk about realistic material screening for CO2 capture, in particularly the impact of water. So continuing on from our last presentation. And just want to give you a little bit of an outline of what I'm going to be talking about. So first, I'm going to present a little bit about the impetus and challenges for CO2 capture. What are the conditions that are of most interest at the moment? I'm going to go into two powerful methods or instruments which we've developed here at SMS for material screening for various CCUS applications, in particular the gravimetric DVS and the breakthrough analyzer. And then we're going to go very, very in-depth on one case study of water CO2 co-adsorption on a molecular sieve. So when it comes to carbon capture and utilization and storage, or CCUS, as I'm sure you've heard it in the media, there are a couple of conditions which are targeted as the most pertinent for mitigating the highest emitters of carbon. So here we have point sources, often called post-combustion capture. So these are places where flue gases are emitted. For example, if we look here, where steel is produced, where cement is produced, where coal is burnt, or natural gas. These streams that are currently just flushed to the atmosphere have relatively high concentrations of CO2, so 5 to 40% by volume. This is why they're prime targets for CO2 capture, but also significant water concentrations and secondary contaminants, often in small concentrations or relatively small, like NOx, SOx, ammonia, carbon monoxide, methane, essentially incomplete burning. They tend to be hot to ambient. So as you imagine, a flue gas tends to be pretty high temperature, so much above 200 C, but often they're cooled down. And pressure-wise, it's atmospheric or slightly above atmospheric. Then, as Menjert mentioned, there's impetus to capture carbon directly from the air. So this is called DAC, direct air capture. The challenge is the fact that CO2 in the air has a very, very low concentration. So 400 ppm corresponds to 0.04% by volume. So about 3 or 4 orders of magnitude lower than in point source capture. But also the system has to operate in atmospheric conditions. So it can be highly humid, low temperatures to high temperatures. This has to work anywhere from the Sahara Desert to Iceland. So -30, -40 to 45 C. And of course, everything is happening at atmospheric pressure. I'd also like to mention two approaches to direct air capture. One would be an active approach where air is forcefully passed over a contactor or an adsorbent or anything that captures CO2. Or there's recently an initiative to have sort of passive CO2 capture, for example, using setting of cement to capture CO2 from the air and act as a CO2 sink. But also, besides these particular process parameters, there are many more process-specific conditions that are encountered during a process. So the way that these two processes are being run in practice is either temperature swing, pressure swing, vacuum or moisture swing adsorption. So this is how to desorb the captured CO2 from the material and regenerate it for a new cycle. And in here, there are many conditions which can be encountered. So high temperatures, low pressures, high humidities, extremely high CO2 concentrations if it's desorbed, for example, you're 100%. So the interest here is to know as much about the system with a complete isotherm, complete isobars of CO2. So these are the challenges, and there are a couple of materials which have been used to approach carbon capture. Some of them are more technology, more towards applications. Some of them are already in commercial processes. Others are still in the demonstration or pilot plant stage, and some of them are still in the lab, in the research phase. But there's no one-size-fits-all solution, and different materials would be used in different applications. For example, amine-supported porous materials for direct air capture, or perhaps just solid sorbents, pure solid sorbents, or ionic liquids, or some membranes for post-combustion capture. And then for storage and for mineralization, completely different technologies. There's really no one-size-fits-all solution. I definitely recommend this recent paper about carbon capture and storage if you want to know more. It really puts everything into a very well overview perspective. So with that in mind, let's go a little bit about how to test these materials in realistic conditions, because one isotherm would not be enough. We need to go towards actual competitive CO2 in water, as was very well shown in the previous presentation. And for that, there are two instruments which SMS has been developing, and they're currently hitting the market. First one is the DVS carbon. The DVS carbon is a dynamic gravimetric vapor sorption instrument. For those not familiar, metric means that there is a microbalance which measures the weight of an adsorbate as it takes up mass. It takes up mass as it absorbs either CO2 or water. The reason it is dynamic is because there is a constant flow passing above this adsorbate, which means that it optimizes kinetics and it leads to a faster equilibrium rather than a point-based method. So in essence, we're just monitoring the weight as there's a change in concentration or a change in pressure or a change in temperature. So these are the variables which can be scanned, concentration or temperature, or both. And this can be explored in a high temperature range, and depending on the system, you've seen the vacuum before, but in the carbon is a flow system. So it means that there is always a continuous flow of inert or as inert as possible carrier gas. To note that the sample amounts can be quite small, so this is very suitable for research applications where you might not have more than 50 milligrams of sample at one go. And this is a general overview of the technique where you have the sample absorbing, in this case, water. There's a change in the concentration of water as a function of time. We've seen the mass uptake, the decrease in mass as there is desorption, and from the processing of the kinetic data, you get an isotherm. This is the schematic of the devious carbon. Now, what is special about the devious carbon is that it can combine a stream of CO2 with a stream of water saturated carrier gas. So you can do either a component or single component in a carrier gas experiments, or an exploration of different concentrations of both CO2 and water. So if we look at the schematic itself, we have the stand here, microbalance. This is where the sample is, the local heating. And we have the two mixing sides. We have CO2 mixing on this side with a patented speed of sound sensor to know exactly how much CO2 is being generated. And on this other side, we have a water reservoir, which mixes a wet and dry stream of nitrogen, also with a probe, make sure you know exactly how much water is being introduced. These two streams are mixed together and to generate the flow that the sample is seeing. There is also on the side a switching valve here, which allows the carrier gas to be switched from either a pure nitrogen in this case, or a carrier gas with a pre-calibrated concentration of CO2. What this means is that different concentrations of CO2 are accessible. There is a high concentration from 0 to, I think it's best if I go to the next slide. So two concentrations can be accessed. There's a high range, so from 0 to 100%. There's also a low range of concentration, so a ppm level. So this can be applied both to direct air capture or post-combustion applications. No, since it goes up to 100% pure CO2, can also be applied to these edge cases like desorption. Water vapor can be generated in the range from 0 to 98%, and of course both of them can be mixed to have a stream that contains both CO2 and water in different levels. Temperature ranges from 5 to 85, the temperature of the incubator. So 90 or 85 RH can be generated up to 5, so high temperatures, high humidities, but also the local heat of the sample, we can go higher in temperature at the cost of humidity. There is an in situ activation of the sample up to 306, and an option to introduce ppm level contaminants. So if potentially you'd want to introduce a third contaminant, the ppm level SO2, that is also possible to have, let's say, 3 components at the everything looks at atmospheric conditions. So now I'll just give you a couple of examples of data from the DVS carbon. I won't dwell too much on them because I think the more interesting is the exploration of the molecular sieve, which is coming up later, but just want to show you a few graphs. So this is, for example, the water isotherms that are recorded. So 2 samples, we can see the kinetics of water sorption and adsorption. We can see the mass increasing and decreasing in function of time. These are processed and can give you the isotherms as a function of humidity, so uptake as a function of humidity. It's pure water, there's no CO2 at this point. This is pure CO2 absorption, so well, CO2 in a carrier gas. So this would be how a CO2 isotherm looks like. We have the same sort of setup, adsorption and desorption on 2 different samples. One has quicker kinetics, the other one has a bit of a higher, a bit of a slower uptake. Then these are the resulting isotherms as a function of CO2 volume concentration. CO2 isotherm is at a different temperature. This is a cobalt, so from 55 to 40. So this can be used to calculate, for example, the heat of adsorption. And a couple of examples with low pressure concentration, low concentrations of CO2, so ppm level, in this case 400 ppm. and this is where we have 400 ppm plus water on top. So we see here that the sample is exposed to 400 ppm. There is an adsorption, and then what's happened is there is a water introduced on top of CO2. So again, co-adsorption, CO2, low concentrations, and water. Yeah, oh, there we go. That's the water. That's where the water is being introduced. Also, a couple of examples of mixing from the two sides, from the CO2 and water. These are two experiments in different configurations. One where the water was first introduced. The CO2 was introduced at 30%, equilibrated, and then water isotherm on top, or the other way around, where we have a full CO2 isotherm recorded with a background of relative humidity. So we can see in green the CO2 concentration, in blue the water concentration and the mass. So introduction of 30% CO2, which is being kept constant as water is being ramped up and down. And this is the other way around, where we have a background of humidity, and afterwards CO2 is being introduced on top. Okay, just CO2 is being introduced on top here with the desorption. So to summarize about the DVS carbon, it's a powerful gravimetric instrument adapted to screening CO2 capture materials both in post-combustion and direct air capture conditions. Going forward, a second instrument I want to talk about is the BTA Frontier, which is a breakthrough analyzer. It's a self-contained breakthrough analyzer adapted to various gases and vapors. Now, what is breakthrough analysis and how does it compare to gravimetry, to DVS? The theory is quite straightforward. Is you have a column of a material, which is a packed column, and you're introducing one or more gases or vapors or mixtures. And at the end of the column, there is a sensor that monitors concentration. So if you can think, you have a step change in the concentration from nitrogen to up 1% of one concentration of CO2, and you're measuring how long it takes for this to reach the end. When it reaches the end, you can calculate the amount adsorbed onto the material in the column. So this is how the data would look like. This is a breakthrough curve. Here at the start is the column is completely empty, so we see the concentration at the outlet as the experiment is started. As the experiment is started, the concentration of the active component, and let's say this is water, is 0. Then the front moves through the column. It saturates more and more of the adsorbent until it breaks through, which is what gives the method its name, and it starts to be recorded. There is a little bit of delay until the concentration at the outlet reaches the concentration at the inlet, as the front progresses through the column and more of the material is saturated. So by looking at this curve and integrating this curve, you see this shaded area that corresponds to the uptake of this porous material for water. So this is a way of also calculating uptakes. But also it gives you a little bit more information about process parameters. If you're thinking about something like a filter for toxic gases, you don't want the filter to act. You don't want to study the total equilibration time. What you want to know is when you start seeing the toxic gases coming out of the filter. So this is more important from the process side. The breakthrough time is more important for the process side than the equilibration time. And the shape of the isotherm, the shape of the breakthrough can give you information about mass transfer and kinetics of the particles and of the absorption. These are the specifications for the breakthrough analyzer, the BTA Frontier. So we've used our expertise in vapors and gases to have 3 different gas or vapor inlet sources. So it can be CO2, it can be water and other volatile organic compounds. Water vapor generation and other vapor generation in 0 to 90 RH. Everything is placed inside a temperature controlled environment. So this is what enters your column. The column itself is in this oven here. It's a small column, so the whole system is adapted to very small amounts of sample. It's again a research instrument. It's 10 to 1,000 milligrams of sample, depending on the sample volume. And at the outlet, there are a suite of sensors that are tuned for particular gases and vapors. So there's a dedicated CO2 sensor, there's a dedicated water vapor sensor, there's a dedicated volatile organic compound sensor, so a PID sensor, as well as a thermal conductivity detector. The idea with this suite of sensors is that it gives you an instrument that is batteries included. Normally, you would need to connect a mass spec at the exit and do complex calibrations to determine what concentrations the mass spec can actually read. Also, mass spec is not the most cost-effective instrument, let's say. So this suite of sensors would give you all of the capability for CO2, water, organics, and the use of a TCD for measurements of different gases without the need of a mass spec. The sample can be regenerated in situ up to 300 C, and this all comes in a small, compact bench footprint with all the software that is needed to analyze breakthrough curves. And this is a little bit of the schematic. We see here the gas inlets, the solvent reservoir, and the column with a bypass as well, and the suite of sensors after the column. Just a quick example. These are just 2 breakthrough curves recorded at 2 different temperatures, just to see the influence of temperature on the breakthrough time of 50% relative humidity. So we can see as you increase the temperature, the kinetics are much faster, so everything breaks through earlier. And also, as you increase the temperature, 50% relative humidity corresponds to more water in an absolute way. So it not only happens faster, but also there is more water coming in. So the breakthrough time is halved. Okay, to summarize about the breakthrough analyzer, it is a battery included breakthrough instrument, and it is capable of recording true multi-component data, which I will go to next, and kinetic information with CO2, water, VOCs, and much more. So one thing to note, and as we'll see in the next section, the BTA can be used to measure real multi-component data, as opposed to a pure gravimetric or a volumetric instrument. Okay, so now we can go and use these 2 instruments in a real-world application, in a case study of post-combustion capture with the molecular sieve. You might have heard about zeolite 13X. It's a fairly standard material. It's a sodium exchange forgesite type zeolite. So this is the crystal structure. It's more often found as pellets. So you might have seen something like this for water drying. It is very microporous, so it's an effective window of around 0.9 nanometers, and it is commonly used in gas separation applications. So oxygen generation, gas drying, desulfurization, it's a very common material. But considering it has high interactions for water, but also for CO2, could it potentially be used for post-combustion capture? So the first thing that one might do would be to measure a CO2 isotherm on the material. And this is a CO2, the corresponding CO2 isotherm. You can see it's a type 1 isotherm, and it has a reasonably high uptake of CO2. So at 100%, it is about at 100% CO2, it's about 15% by mass. And if we look at the range for post-combustion capture, let's say around 10 to 20, it also has 10 to 15 weight% in this concentration range. There is a slight irreversibility in the CO2 sorption isotherm, which is interesting, because it means that there are some either some defect sites or some CO2 that cannot be recovered. But overall, it seems like a promising material. Yeah, this is a 15% weight uptake is something that you would potentially use in a process. Let's look also at the water isotherm. Now, the water isotherm is definitely a type 1, very, very high, very, very steep knee here at low concentration. So what we see is that even at 0.5% relative humidity, which means a very, very low relative humidity, this material takes up 20% or nearly 20% in water. The water is really strongly absorbs. There are very high affinity between water and the ZLI13X. So if we try to do it, when we're looking at the desorption branch, what we see is under a pure nitrogen flow, it's nearly impossible to regenerate it. What happens is there's nearly 15% of water still trapped in the material, no matter how long you wait. So it's clear that there is a strong interactions towards water. One thing to note is that relative concentration, relative humidity, corresponds to much lower volume percent concentration. So if we think about 100% relative humidity, that means 100% of the capacity of a carrier gas to carry water at that temperature. So at 25 C, 100% relative humidity corresponds to around 3% by volume. So just one thing to note is when we're comparing two isotherms of relative humidity and CO2 with volume percent, it's not exactly apples to apples. And these are just the two isotherms compared. And what we know now that water appears to have a very high uptake. So we would think it potentially would interfere with CO2 sorption, but it's not necessarily the case. As we've seen in the previous presentation, some sorbents, like amines, actually have a synergistic effect. Water seems to increase the uptake of CO2. It could also be that water and CO2 compete for two different types of sites. So there can be a combined effect. So water absorbs on the water sorption sites and CO2 absorbs on the CO2 sites. There's no interaction between the two. So while we can potentially presume that water will have an impact, we don't know beforehand what it could be. Unfortunately, water has a negative impact. So this isotherm here at the bottom, you can see it, is recorded with a constant 5% RH throughout the entire isotherm. So this was recorded in the DVS carbon with a constant background relative humidity of 5%. And then afterwards, putting CO2 in at these concentrations. What we see is that the uptake compared to the original isotherm, when CO2 is put in, seems minimal. It's 0.3 weight percent compared to 15 to 20%. So it seems that CO2 does not absorb on top. But as we've seen, it's a little bit more complicated than that. There are some assumptions made. So in the previous isotherm that I showed, the assumption was that when CO2 is added, it does not displace any water. And if we zoom in a little bit on the kinetics, that does not seem to be the case. This is the entire kinetics of the previous experiment. We have in red the concentration of water. So this is the pre-saturation with water at 5% relative humidity. The whole experiment is being kept at 5% relative humidity, and then CO2 is being dosed on top from 0 to 90%. And if we zoom in to when CO2 is introduced, we see that there is definitely an uptake, but then there is a slow equilibration step where something is happening. So there is CO2 which does displace some of the water, but we don't really know how much. And just taking the equilibrium values here and saying that they are the uptake of CO2, so the isotherm that I've shown on the previous slide, the assumption doesn't hold anymore. Just quick thing to note, this experiment was performed as 40C to increase the kinetics, but you can see all of these also in experiments at 25C, so where all the other isotherms were recorded. So the way to approach this is through breakthrough analysis. Breakthrough analysis, you can monitor concentrations independently at the outlet. So you can put in a mixture of CO2 and water, which is exactly what this breakthrough curve shows, and record the outlet concentrations of each independently. By integrating the two curves, one can obtain actual multi-component uptakes for each of these two components. So these are 3 breakthrough curves, also on a zeolite 13X. We see CO2 breaks through quite early, while water takes a longer to break through. Again, it shows that there is much more affinity for water. Just as a side note, this is at 20% RH and 3.5% by volume CO2. There is very good repeatability between cycles. And one other thing to note is that when it comes to the concentrations that are measured at the end, the concentration of CO2 seems to go above the initial concentration. So after CO2 breaks through, we seem to have more CO2 at the outlet than we're putting in. This is what is called a roll-up effect. And the reason behind this increased concentration at the outlet is that the water that is coming in at the inlet of the column displaces CO2. So it kicks out CO2 from the adsorbed phase. So what is being read at the outlet is the inlet concentration plus the CO2 that is being displaced by the water. And this is why the concentration goes above unity at the outlet while water is being adsorbed. And as water breaks through, it goes back down to the same concentration as the inlet. So one needs to be very careful when integrating these curves to find out the amount adsorbed, that they integrate this part at the start, but also this negative CO2 that is being displaced. So all of this curve has to be integrated in order to obtain an accurate amount of CO2 adsorbed. If we stop here, it is not going to be a correct picture. Just a quick mention to show that I mentioned before that there is no need for a mass spec from the BTA frontier, but this is just a graph that shows that if you do connect a mass spec at the outlet, you get the exact same results, although a bit noisier because mass specs don't really like water that much. And here are the results of the integrations of these two curves to obtain the uptakes of each component. This is in weight percent. On average, we have around 0.5 weight percent CO2 and 23.4 weight percent water at these levels. If we remember the isotherms that were recorded from DVS, at 3.5% volume CO2, we would get about 7.6% by weight CO2 uptake. So this is in the pure component in just CO2. if we were to look at the isotherm of water at 20% relative humidity, we would in theory get 24.4 weight% water. And if we put both of them together in the co-adsorption in the BTA, these results show that the amount of CO2 is diminished massively, while the amount of water stays pretty much about the same. But there is something to note here, and this is why I put the standard deviation. The integration of this curve has a bit of error in it because of the noise and the length of time that you have to integrate. There is just a small amount of changes that add up. So the standard deviation is 0.3 weight%. So in this case, we're reasonably sure that it is less than 1% CO2, but we still don't have a full picture of how much exactly it is. It is 0.5 plus minus 0.3 or 0.4, depending on how much degree of confidence you wanted to look at. So even though it gives you a good picture of co-adsorption, the error bar over here is much higher than you'd want. So one way to go about to obtain an accurate CO2 uptake in the presence of water is to combine the two results, the two instruments. So when this is an experiment in the DVS carbon where we have the same zeolite 13X. There is a dose with CO2, so it's 7.5%, and then water is introduced, and then this is the total in the same conditions as in the breakthrough analysis. Here at the end, we also see that if we switch to CO2, there is some mass loss, but the point that we're interested in is this one. This is the same point, excuse me. This is the same point as here in the breakthrough analysis, where there is 20% RH and 3.5% CO2. We know that from gravimetry, which is very, very accurate and independent of other variables, that the total CO2 and water uptake is 24.4% by weight. From the BTA, we know that the CO2 uptake has a little bit of error, but the water uptake has almost no error in it because of the long time it needs for its breakthrough. We can be very certain about what we're integrating. So from the breakthrough analysis, the total uptake of water in these conditions, we are very sure that it's around 23.4 weight%. And one thing we can do is we can take the difference between these two and we can obtain an actual amount of CO2 adsorbed, which is around 0.82% by weight. If you want to learn more about this approach to determining uptakes, there is a very good paper from the University of Alberta from Arvind Rajendran's group, where they also measure CO2 and water on zeolite 13X. But to highlight is that there is no one method that can get you what you want. So to conclude for this study, water does reduce CO2 uptake by about a factor of 10. So we've pretty conclusively proved this by using both breakthrough analysis and gravimetry. There's one thing to note is that the kinetics of CO2 adsorption and the kinetics of water sorption are vastly different. CO2 appears much faster than water, which takes a lot longer. So perhaps not everything is lost. If we think about this material, maybe it can be used in a kinetics-based process rather than in an equilibrium-based process to separate CO2 and water, to still use it in a carbon capture process. But my goal was to convince you that it's not a simple matter. Nothing is simple. In order to really evaluate a material for carbon capture applications, if anybody tells you that it is, then you need to ask what are the assumptions that they are making in their experiments. And I think it's pretty clear from both this case study and the previous presentation that it's really a complex matter. And a combination of techniques are required to fully assess a material. So the ones that I've talked about here are DVS, the DVS carbon, and breakthrough analysis. But going forward, there are many other things to look at from a holistic perspective to obtain these co-adsorption amounts and really evaluate a material from the point of view of the impact of water, the impact of other contaminants, the recoveries, the impact of temperatures and oxygen, etc. So it's not really simple, but hopefully we're getting there. So I'd like to also let you know that there's a paper that's going to be soon coming out on evaluating solid sorbents for CO2 capture. So which gives us a little bit of the best practices on how to best evaluate solid sorbents. And I'd like to thank the SMS collaborators and the team, and also to thank you for listening.
Thank you, Paul. Thank you very much for your very explanatory presentation on these new techniques that SMS has developed. Any questions? We do have just a couple of minutes, and we need to move on to our third presenter, Dr. Ahmed Rezk. Any questions, please? I can unmute you all.
Hello.
Hello, hi.
Hi, okay, glad you can hear me. I want to ask a quick question regarding heat absorption and measuring the actual heat of the absorption processes. Which of these two methods, the DVS and BTA, can be used to actually measure this heat? And is that something that's doable with these systems? And then which of SMS's products would be best suited for actually giving a detailed measurement of absorption-desorption process?
To measure the heat of absorption, the most straightforward way is DVS. So with the DVS carbon, it can be measured a couple of isotherms at different temperatures. You could apply the Clausius-Clapeyron equation and measure the heat of absorption as a function of loading. I would say that for heat of adsorption, the ideal application, the ideal instrument would be the DVS vacuum, as it uses a pure stream of CO2 or a pure stream of water. So that will give you heat of absorption that's, it's not a heat of displacement, just in case there is a carrier gas influence.
Sorry, I can't do this. So
yeah, it's fine. Just present like this, Ahmed. It'll be fine.
Okay. Right. So good morning, everyone. Sorry if sorry for the technical glitch. So my name is Ahmed. I'm a senior lecturer of thermal fluid sciences at Aston University. My main research is sustainable heating and cooling, and the application I directly use the DVS equipment is for heat storage material characterization, and the application is sorption heat storage. You might be aware of what is sorption heat storage. So sorption heat storage is a device you can store the heat in a form of sorption potential, not heat potential or temperature different potential. So assume that we have a reactor here, and this reactor contains a sorbent material like silica gel, zeolite, activated carbon. And when you have surplus heat, so you can use this heat actually to dry up this sorbent material, and then because you might use water, you might use something like ethanol, methanol, or any other gases. So you just store it in another storage. And when you expose this back to the sorbate, to the adsorbent material, the absorption heat will can be retrieved again. So this way we can charge and discharge. The main advantage actually of this sorption heat storage is that because we don't have temperature difference between the storage itself, between the charging and discharging mode, so you can charge the heat for relatively longer time compared by phase change material or any sensible heat material like brick or water tanks. So if you have surplus heat in summer, so you can use it in winter. That's the main advantage of sorption heat storage. The main challenge you might know and you might not know that we have a lot of material that can work well with water, for example, if we're going to use water as a working fluid. But the problem is this material thermally very bad conductive material, and the rate of transfer heat, the heat transfer is very slow. So it is like insulation, like silica gel and zeolite. So you can heat them, but the rate of heating and cooling is very slow. So if you have surplus amount of heat and you need to capture them very quickly or release them very quickly, depends on the demand, this would be the main challenge. That's why I develop new material. My goal actually is developing new material, or to be precise, composites, and we look at chemosorbent material integrated with some other thermoconductive material like carbon-based material, and try to solve this issue actually. So this is the equipment I use, which is DVS resolution, and this is the main advantage actually of this equipment, and this can be considered one of the main equipment I use here at the university. So these, I'll try to make it quickly because I have teaching now. So I developed one of the materials I developed actually is using some salts related to ionic liquids and some carbon-based material as a host matrix, and we tried actually to generate different composites, and the variation between composite and another is the concentration of the salt into the host matrix. So we can look at actually here, which is the isotherm for the generated for the developed material, which is the first step to characterize the material. And in this case study, I present this newly developed material actually working with water and ethanol as a working fluid. The reason of using water, because water has very high heat absorption compared by ethanol, but ethanol can be handled at sub-zero operating condition. So if we look again into the system here, so the heat source comes from the evaporator component, and this heat source could be from underground heat or could be from the ambient. So if we look at heat, the ambient heat in winter, where we need the heat storage actually to operate and give us heat, which is a discharging mode, the ambient can reach to sub-zero. So today the temperature in Birmingham is 1 or 2 degrees C, and some areas outside the city center reach to 0 and -1. So the evaporator to be operated under the ambient condition as a heat source wouldn't really work, and to invest in underground heat, it might cost you a lot of money. That's why we can look at using ethanol to work sub-zero or at sub-zero condition, which will be ideal actually if you saved some heat from the summer and you want to use it today. So this is the first step actually, is looking at the absorption isotherms, which tells you what material works best in terms of the equilibrium uptake. But as most of you know that it's equilibrium uptake, so the material takes time to reach this condition, but the kinetic is also important. But again, we need to look at the absorption isotherm itself, and we're going to look later how the kinetic comes into the context. So we characterize the material, and we have a benchmark material, which is silica gel. Most of the material generated are type 2 isotherm with water. So on the left hand side here is water. On the right hand side, the materials developed working with ethanol as a working fluid, which shows more type 3 isotherm. The next step, actually, we need to look at the repeatability and stability of the material. So we apply extreme partial pressure on the material between 0 and 90%. Sometimes you can call it partial pressure, sometimes you can call it relative humidity if you're coming from humidification and dehumidification industry. So we apply this extreme, and we can see that some material are very stable at low and high concentration of water vapor and ethanol, right? Like this material we can see. This material is, no, we move to this one first, sorry. So this one is stable. We can see it can absorb and desorb the water vapor, and the composite physically still the same without any change in the geometry. Okay. If we look at high concentration actually of salt into the host matrix, what we can observe that we can see some sort of agglomeration and ends up with the salt dissolved and leaves the host matrix. When we look at the applicability of this material, it is not really very applicable because when we back it into the adsorption bed, it might leave the salt might leave it will leave actually the matrix, and you left with empty matrix, and the salt will go everywhere in the machine. So we can't really use this. So this is one of the important features. We can look at the physical stability of the material and if it is applicable or not. Although the stability curves here shows very well trend and there is no degradation in the absorption-desorption behavior between the extremes, but still the material not applicable. We compare it with 10%, for example, concentration, 10% is better. However, when we look here, the 10% is low in terms of the endotherm. So if we look at the practicality of the material, we might go for 10%, not the high concentration with 30%, which achieve high absorption rate. The second characteristic or the second property we measure is the heat absorption. So we measure the heat absorption for this case study. I measure the heat absorption of the composites against water and ethanol. And it is important actually to look at the heat absorption against. So the y-axis here is the heat absorption, and x-axis is the concentration of the water uptake. And we need to look at whether the heat absorption is stable across the surface coverage or varies, which guide us actually where most of heat can be gained from the isotherm. Because later we're gonna put this cycle on the isotherm, and if the cycle occurs at the heat absorption, high heat absorption region, so we have a good combination. Otherwise, we need to think about how to utilize this material better. Although actually the main sorbent material here is the salt itself, not the host matrix. The host matrix was carbon and doesn't absorb or dissolve water vapor. But the dispersion actually of the salt within the host matrix had an effect. So for example, here at high surface coverage, we have higher heat absorption, which makes sense actually. It's a chemosorption effect, and the dispersion actually cause more active sites for the absorption. So we can find that the heat absorption increases at higher concentration. So at some composite we can find trends, proper trends, and we can see actually when we look at the pure material itself without using the host matrix, some composite shows, some salt shows constant heat absorption. But again, we're gonna use the solid composite in our in this application, this particular case study. So now I move to look at the cycle, and this cycle sketched on the isothermal graph. And in this case study, we looked at using ethanol operating above zero temperature from the evaporator side, and below zero temperature in the water side, and water vapor which has to work above zero anyway. We can see that we have bigger size of cycles, so the net cyclic uptake potential for the ethanol is very high. If I have high heat absorption, it would be happy days. So high heat absorption, high uptake, it means that I have high heat can be stored between seasons. If I have here actually low uptake, so yeah, we have high heat absorption, but the uptake is very small between this operating condition, between these limits. Here actually water is something in between, but when we look at the heat absorption for water in this case study, we found that the heat absorption of water was higher than ethanol. So we can find a conclusion from this figure that, yeah, I can go to this cycle, the red cycle, or the black cycle, but it is not feasible enough actually to look at this blue cycle. Okay. You can find actually, we'll try to link between the material properties and the application part of the research is not only the material characteristics. So now we move to mimic the cycle operation actually by changing the departure pressure in the device to represent the operating temperature during the absorption and desorption. So we change the departure pressure to represent this. So here actually we have high departure pressure. It means that we have discharging. So we have low departure pressure, we have charging, right? So while we charge, we dry up the material. While we discharge, we humidify the material or apply the sorbent to the sorbate. And this is the time actually while we can see how the kinetic works under the realistic operating condition, not only by setting the departure pressure at 10%, 20%, 30%, and so on, which is a step curve. Step curve is useful, but in this particular application, we need to find how the material behaves in terms of the kinetics between the actual or quasi-actual operating condition, which is mimicked in a way by the departure pressure. And by the way, that temperature difference between the reactor and condenser or evaporator, the driven force is always actually the departure pressure generated by the temperature. So it's very accurate presentation of what we can see in the device itself. But for the material, the device consider actually some other heat transfer issues. So we can find actually the pure material is still behaving the best, and we have combination of good thermal performance comes from the host matrix because it was carbon-based material near graphene, but the amount of the salt, which is the main active material, is not sufficient enough to give you this heat compared by this heat stored compared by the salt itself. But this is a case study. We show how we use the material as the equipment capacity to study this material. And now we know how much uptake and how speed this uptake happens, so we can quantify almost how much heat can be stored in this heat storage application. As you can see, when we did this analysis, we used change in the departure pressure. We didn't consider actually the heating and cooling, and the main purpose of developing this composite was to stimulate the heat transfer to aid or support the sorption potential. So here actually is another form of investigating how the material will respond to the temperature. So we used the local heaters in the equipment to locally heat the material itself, which represent what happens in the heat exchanger in the reactor. So we can see actually the response towards to heating at least. Cooling might be challenging, but heating, we can get away with heating and can draw a good conclusion out of it. So there are other case studies. So this one is still under publication, and we have we submit the patent for the material itself. So there are some other applications using the equipment. And if you have any question about this application or this case study, please drop me a line on the email. And thank you. I'm sorry for the technical glitch happening.
Thank you very much, Ahmed. If you can share your presentation, that would be great. I know you're watching now. If there are any questions, then we will let you know. Yeah.
Please, I have to leave now because it's 7 minutes after the lecture time.
I understand. If you can send me your presentation, that would be great. Thank you very much.
Thank you so much. And sorry for rushing it.
No, it's okay. I understand. Thank you.
Thank you, Ahmed.
Thank you.
And now, Connor Hewson. He's our application scientist, and he's going to talk about surface properties using our inverse gas chromatography surface energy analyzer. Thank you, Connor. We cannot hear you, Connor.
Hello, can you hear me now? Can you see my screen?
Yes. We can see the screen.
Fantastic. So thanks everyone for coming. As I said, I'm going to be the last speaker of today, and I think that is quite fitting because I am now going to be talking about the most different methodology and the most different instruments of all four speakers today. So for most of today, we've been speaking about dynamic vapor absorption, which of course is a gravimetric technique used to determine the mass increase or decrease as we're introducing water or we're introducing organic vapors in different flows, in different concentrations at steady states. Now I'm using a very different technique where I'm introducing those sorts of gases, but now as an injection, as a pulse, rather than as a continuous flow. So I'm first off going to start talking about an introduction to absorption techniques, and then I'll really zoom in on the differences that you'll see between inverse gas chromatography, which is the topic of my discussion, and dynamic vapor absorption. So much as we've seen for all of our presentations today, we will be characterizing solids no longer using the more conventionally done approach, which is using energy as a probe. So for something like a spectroscopic technique, you're going to be using the balance between that which is absorbed and that which is emitted, and that's going to give you some analytical, structural information about the material that you are irradiating that energy onto. Now, what we're doing in dynamic vapor absorption and in inverse gas chromatography is we're introducing molecules to our sample, we're seeing how it interacts, and from that interaction we can infer some thermodynamical, some chemical, and some structural information about the material. Because we know the probes that we're introducing, we know their properties, we can then use that to predict the chemistry and the structure of the thing we are investigating. So when I introduce my molecules over my surface, they can interact in a number of different ways. So they can interact by just absorbing onto its surface, and that's what we would call molecular adsorption. When we're looking at this from dynamic vapor absorption, from a sample that would only be going through surface absorption, we would expect very little uptake, anywhere between 2% to close to 0.1%. That would be as a result of just surface adsorption. Anything where you're going above that 2%, that 1% mark, that's when you are now getting the bulk of your material, absorbing a large amount of those probe molecules. So your water, your organic vapor, has gone into the structure. It's entered its lattice, or it has found those amorphous regions where it can have higher uptake than usual. So there are a few ways in which we can measure the influence of our probe molecules. We can see how the mass of this sample changes as we're introducing introducing these molecules. We can also see how much we inject versus how much we detect. And that way you can get an idea of how much that material is retaining. In inverse gas chromatography, what we want to do is we want to see how quickly or how slowly our probe molecules are going over our surface. So quite a different system to you see with dynamic vapor absorption, but the way and the manner that we are introducing our probes over our sample reflects some similarities. So on this slide, you can really see the major differences between the two most popular techniques that we manufacture at surface measurement systems. So on the left, we've spoken lots today about how this is a gravimetric method, how we're observing mass change as a function of carrier gas versus, probe introduction with a carrier gas, or just probe introduction with a vacuum. Now, the IGC SEA stands for Inverse Gas Chromatography Surface Energy Analyzer. So it is an instrument that has been designed to optimize inverse gas chromatography experiments. And one of the main applications of this instrument is to measure the surface energy of our samples. And here you can see on this slide the real characteristics that we're introducing a probe in isolation, we're passing it over our sample, and then we are detecting it and its intensity as it comes out of our column. And from this slowing down of our probes, we can collate multiple probes at multiple concentrations together, and we can get surface properties of our sample. So I'm going to give a general introduction to the technique overall and how we can use this to analyze the surfaces of our samples. So as a technique, inverse gas chromatography has been around since the 1960s. However, it took until 1999 for the first commercially available inverse gas chromatography technique to be designed. And this previously, before the commercialization of this technique, these experiments were done on traditional analytical gas chromatography instruments. Now that means that they were not designed to keep the column uniformly heated throughout. They were not designed to inject very well-controlled and small syringes of our gases into the system. And that is what is being optimized in a commercially available unit. It is introducing temperature equivalently throughout your sample. It is introducing your probes in very controlled volumes of injections, and it's ensuring that those probes are injected in the gas phase and not in the liquid phase. So it has been completely optimized to do absorption isotherms, to measure the heat absorption, to measure solubility parameters, glass transition points. But what I will be talking about mainly today is how it can be used to measure the surface energy and the surface area of our samples. So some of you may be wondering, what is inverse gas chromatography and how does it differ to analytical gas? So on this slide, you can see here, you can see the main differences between these two. So above we have a situation which would be going on in analytical gas chromatography. So we have a mixture of gases, and we do not know those gases or how much of those gases are in that mixture. And this is what's under investigation. Our mobile phase is being investigated. The thing we do know very well in this scenario is our stationary phase, our solid phase. We know that this will be something like silica. We know its particle size distribution, its material. We know its dispersive contributions. Therefore, it's very good at separating out my gases. So from the area of from the location of these peaks and their retention times, I know what that gas is. And from the intensity of these peaks, or the area under the curve, I know how much of that gas there is. So I've solved the puzzle. I found out what it is and how much of it there is. Now, in inverse gas chromatography, what we're doing is we are swapping what we know and what we don't know. So now what we know very well in inverse gas chromatography is we know our mobile phase. In this scenario we see down here, we know that we are injecting no-name. We know exactly the concentration we are injecting. And what we don't know is now our sample being investigated. We don't know the stationary phase. So this is our sample that we packed into our own column. Now, if I change the concentration of this probe I am injecting, I am going to get very slightly different profiles of my retention curve. And it's from these slight changes from different concentrations that's giving me the properties of the surface. So I can repeat this with a number of different probes, put all of that information together, and then I can get some physiochemical properties of that solid and of that surface. So on this slide, you can see a summary of all of the things that we can determine using this technique. So we can determine the dispersive surface energy, the polar surface energy. We can map it as a heterogeneity. That's been mentioned previously before in dynamic vapor absorption. We can also measure the heat, the enthalpy and entropies of adsorption using this technique. We can also get a few other things like the surface area, the acid and base interactions of my surface, monitor phase transitions. We can look at permeability and solubility and the thermodynamic work of cohesion. Now, in today's presentation, I will not be going through all of these properties. I will be going through just surface energy, dispersive and polar, and the heat of entropy of absorption. But if you'd like further information, please get in contact with us at the end of this presentation, and we'll happily talk about some more case studies where the listed properties you can see on the screen will go in further detail. So this is all of the work a user would really have to do in sample preparation. It's a very simple scenario of putting a siliconized glass column. You then put some glass wool into the bottom of this column, and then we pack our sample within. So anywhere between 10 milligrams to 250 or 2,500 milligrams would be appropriate for this sort of experiment. And it really does depend on the surface area and the activity of my sample. So a porous material such as a moth or a zeolite would need a very small amount of sample due to its high surface area and high activity. Something with a low surface area, something like a fiber, that would need a lot more of my sample. So I am maximizing the interaction between my probes and with my sample. So it's very simple sample preparation. You put in your glass wool, which is non-interacting. You have your siliconized column, which is also non-interacting. And then the only thing in my column which will interact with my probes is the sample that I put in there myself. So no special preparation, and it's non-destructive analysis. So as long as your sample hasn't gone through any phase change, as long as it hasn't been destroyed by the introduction of my probes, then it isn't destructive and it can be used for further analysis later down the line. So for a user, you would pack your column with your sample of interest. You would select the probes that you're introducing. You would select the concentrations that you introduce them at. And then from that, you can determine the properties that you wish to determine. So from multiple isotherms plots with multiple probes, you collect that together and you get the properties that you desire. So finally, you can see the instruments on the screen. To our right, you can see what an IDC-SEA instrument looks like. So we've got a few features that we find here. In the middle, you can see the column oven itself. And either side of this column oven, we have our solvent reservoir drawers. So in each of these reservoir drawers, we can hold 6 different solvents. So that means we can have 12 solvents in total. Now, how we introduce our probes is that from the saturated headspace of these probes, we make a gas injection. So a little tube will go into the top of this reservoir. We will flow out from the saturated headspace, and then those probes will be diluted with our carrier gas. And that in this case will be helium or nitrogen. So what this will do, this will introduce these probes from the top of this column. So at the very top of the oven, we would have our sample packed in the middle here, and then from the end here, it would pipe our probe molecules into a detector, which would be a flame ionization detector. And then we can measure the amounts and the time taken for our probes to elute through our column. You'll also notice that we can do 2 columns within this system, so we can run 2 experiments consecutively and not simultaneously. So this oven is capable of doing an experiment from 20 degrees C to 150 degrees C. Now those temperatures apply to actually doing the entire experiment at that temperature, or they can also apply to pre-activation of the sample to do before we do our experiment. Much like we saw with dynamic vapor sorption, the influence of humidity can have a really large impact on uptake, as we saw with the gravimetric method, but they can also have a significant impact on the surface properties of our sample. So we can measure the influence that humidity would have on the surface area and on surface energy. And the way we do that is by committing one of these reservoirs to water. So I can now do an experiment with a constant humidity background. So I can find out my surface area, I can find out my surface energy as a function of a constant humidity there throughout the experiment. So we have very user-friendly software analysis, very simple to use. And down here you can see some pictures of different samples that are suitable for this sort of analysis. So it really is as simple as any sample that you can place into a column, that you can pass a gas over without building pressure. This would be suitable for inverse gas chromatography. So the concept of inverse gas chromatography is all relative. Now what I mean by relative is that you must make corrections for your dead volume. So what do I mean by dead volume? This is now a time that we can register as a result of a gas which we deem to be non-interacting. Now, in this case, this is methane. So we will do an injection of methane, and we will see the time that it takes to elute through the column. Now, this is being done to calculate for that dead volume. So the area of the column which has no sample within it, the area of the column that's being occupied by our sample. So it's accounting for those volumetric effects. Now, everything that we get as regards to retention times from our interacting probes is now having this dead volume taken away from that. So now what we get is this value of net retention time. And it is this net retention time that is directly relates to that strength of interaction between the probe molecule, such as hexane, heptane, and octane. That net retention time is directly related to the strength of that interaction between the probe and between the solid. So the first physical chemical property we need to know in inverse gas chromatography is the surface area. So on this slide here, you can see the different ways in which you can make a BT determination. You can find out the surface area of your sample. So here we can see where dynamic vapor sorption and inverse gas chromatography excel in this sort of measurement. And here you can see how it holds up, again, a more commonly adopted nitrogen absorption technique, which is a volumetric technique. So you can see the nitrogen absorption technique really excels with high surface area materials. Anything of 100 meters squared per gram, the nitrogen technique does well, especially for materials that are only going through surface absorption or have a very well-defined pore size distribution. However, there are a few drawbacks to using this technique. So first of all is the conditions that are required for this technique. So the nitrogen absorption technique relies on nitrogen being at a cold temperature, so 77 degrees Kelvin, in order for this interaction to be a surface interaction. And it also requires vacuum drying prior to the nitrogen being introduced. Now, those harsh conditions, those low temperatures, those vacuum drying conditions, they very well could cause a phase transition. they could cause the dehydration of a sample, and they could cause the collapse of some fragile crystal structures. Now that can cause you to change the surface area of your sample before you've even measured the surface area. So it's the methodology of this technique may not suit all materials. Now, when it comes to dynamic vapor absorption and inverse gas chromatography, these measurements are done at ambient temperatures and at ambient pressures. So you are getting a more accurate representation of what that surface area is under the conditions before you have changed them under the harsh conditions applied. Another thing I'd like to highlight is the performance of these techniques for low surface area materials. So nitrogen absorption technique really begins to fail when you get to 1 square meter per gram and lower. Now this has a very high relative standard deviation of 10% for this low end of surface area. And you have to mitigate that by using something like a heavier noble gas like argon or krypton in order for this relative standard deviation to decrease. Now, inverse gas chromatography excels in this range. We have as low as a 1% relative standard deviation for very low surface area materials. So it outperforms a volumetric technique when doing low end measurement. Now on this slide, you can see some of the drawbacks that I have highlighted for the volumetric technique. And there are a few other benefits that we find with the chromatographic technique. I could do BET determination as a function of with many different solvents. So I can do a surface area determination with a hexane, an octane, a cyclohexane, many different probe molecules I can do a surface area determination with. And I also have the ability to use humidity during this measurement as well. So here we have a known BET standard, CRM 170, and it's got a low surface area of 1.05 meters squared per gram. So I precondition my column at 100 degrees C for 6 hours. And after that, I let my column cool back down, and I did at 30 degrees C a octane isotope. So here you can see I was aiming for a high partial pressure to a low partial pressure, and then I find a region where I'm getting a good linear regression within the BET range. And here we can see the value I have calculated from this measurement is in very good agreement with the value we have quoted here. So really showing that we have good performance for the low surface area. Now on this next slide, we can look at the influence humidity can have on surface area. So now we're looking at a similar material. Once again, this is CRM sample. Now this is 171, so slightly higher surface area. And this is a sample of alumina. So we're only going to be exhibiting surface site absorption. And here we can see the really large impacts that humidity has on surface area. So we can see as I go from a dry column to one with 50% humidity, one with 90% humidity, the effects humidity has on surface area is drastic. So at 50% RH, we're getting a small reduction in surface area. Now, when we get to 90% humidity, this becomes much more fast. And we nearly halved, and we have halved the surface area of our sample. And this makes sense when you think of how we're interacting with our surface. Our humidity is interacting with our surface, it's occupying some of those surface sites, and it is competing with our octane. So it is now the apparent surface area that is decreasing as a result of that moisture we are introducing. So to do a surface energy experiment, it is vital that we know the surface area. So we can measure our surface area in an inverse and we then calculate the surface area. We plug in that known surface area back into the instrument, and then we now know the surface of our sample in the column. That means the software knows how much of our probes to inject to achieve a certain surface coverage. And it's with those surface coverages that I can make a surface energy profile. But why do I want to know surface energy? Here on this slide, we can now see a number of different surface scenarios. So we have a very rough surface here that we can see at the top. And this is a scenario that we would see higher surface energy. You can imagine we've got lots of atoms or molecules at the surface of this sample, which are covalently not pleased, which have these dangling bonds, which are non-covalently satisfied. And it is these dangling bonds that are giving it that higher surface energy. You have some very unsatisfied parts of this surface compared to some very satisfied low energy parts of this surface. So we would say this surface, this higher roughness, is giving it that higher surface energy. At the bottom here, we have an ideal scenario. All of our surface atoms are equivalent. They are similarly satisfied. So we would say it's a more homogeneous surface and a lower surface energy surface. And we can predict this energy to a number of different properties. So a material that's going to have higher energy, we would expect it to have higher activity. So if you are a pharmaceutical, you have one batch of an API compared to another batch of an API, we would say that batch that has the higher energy would have the higher activity. So better bioavailability within the body. We would also see a set of particles that have higher surface energy would be more likely to aggregate, more likely to form lumps, and would exhibit poorer flow properties. And when we have a multi-component mixture, we would see that this would have high work of adhesion as well. So more likeliness to bind to other particles of another composition. So within the system, we not only could measure one energy, we measure two energies. We measure the dispersive component, and we measure the Lewis acid base component, or the polarity of bonds. So by using our non-polar probes, our hexane, our heptane, our unduncane, our dicane, these are probes which have no polarity. They will only interact with our surface as a result of van der Waals and London forces. So it's these induced dipoles that are the reason that we're interacting with our surface. So this is how we calculate our dispersive surface energy. It's by calculating that van der Waals contribution that's resulting in the activity of that surface. We can also inject polar probes, so something like dichloromethane, toluene, ethyl acetate, these molecules that have permanent dipoles. And we can use these to calculate the influence our surface has as a result of polarity. So how much ionic species are on the surface? How many polar functional groups are on the surface that are contributing to those dipoles that are going to be causing strong interaction with our polar probes. Now I can add together these two different energies, these two different energy profiles, and I can add these together to get my total surface energy. So I can split my energy into three different areas and analyze them, and I can analyze them separately using this technique. So my dispersive surface energy, I will calculate that at a number of different probes. So here we can see I have injected hectane, octane, nonane, and dicane. And we can see the larger probes are going to go through the slowest. Now, if I inject all of these probes aiming for the same surface coverage, so I've injected enough dicane to cover 20% of the surface. I've injected enough heptane to cover 20% of the surface. Then I can construct this, the alkane line. And it is from the gradient of this line that I get my dispersive surface energy at that specific coverage. Now, if I do this at a number of different coverages, I get a number of different energies. So I did this exact thing at 20% surface coverage, 10% surface coverage, 5% surface coverage, and 0.5% surface coverage. I form this lovely surface energy profile. It is at the most dilute injections that I am analysing the highest energy sites, and it is at the most concentrated injections that I am analysing more of an average surface energy, and I'm filling those lowest energy sites. And from this profile, I can form a distribution. And from here, I can get how populated each of those energy levels are on my surface. So from a very simple methodology of a few alkane injections at a few different concentrations, aiming for different coverages, I can get different energies at different coverages. Now, this similar methodology can be applied to my polar probes. Now, the distance that these probes have from my alkane line when extrapolated backwards is directly related to that polar, that additional contribution to energy that they have as a result of those polar functional groups they have on their structure. And that is how we can quantify the additional interaction they have as only a result of their polarity, with no regard for their van der Waals interaction or their dispersive interaction. And I form a profile that looks like this. So here we see in our green line, this is our dispersive surface energy. With our blue line here, this is our acid and base surface energy, or our polar surface energy. And the green line here, or the red line here, is our total surface energy. So from a simple experiment, I now have formed 3 different surface energy profiles. And I can turn each of these into a distribution to get the population of each of these energy levels. Now, it may be a little bit more useful if we talk about these sort of thermodynamic properties with regards to specific. So the first case study I'm going to talk about today is going to be multi-walled carbon nanotubes. So here we have 3 different carbon nanotubes that we'd like to analyze the surface energy of. So our first one is as received, so one that's had no further modification done to its structure. So we see we have a surface area which has been calculated. We have done its Raman crystallinity, and then we've also calculated the oxygen content within its surface. Then to this same sample, we have annealed these carbon nanotubes. So this was heated to above 1000 degrees Kelvin for an extended period of time to see how this is going to influence its dispersive surface energy and its polar surface energy. And we can confirm that the annealing has had an effect on the structure by looking at its Raman crystallinity. So we can notice the influence that that high temperature annealing is having on the structure. And finally, the last modification we did was oxidized. So we introduced some oxygen groups by grafting on some methoxy groups onto the surface. And we can see that we've successfully added those oxygen groups to these carbon nanotubes by having a look at its oxygen content. And we've increased it by roughly 1% on its surface. And we want to see how that influences the surface properties of our samples. So here we can see the dispersive surface energy profile for each of these materials. And we can see that these different pretreatments have had a significant impact on the samples. So we will start off with our as received. Pardon me. So we can see that all of these samples are heterogeneous. So what that means is that their surface energy is changing as a function of fractional coverage. So that means at the most concentrated injection, the one that was aiming for the highest surface coverage, that has a different energy to my most dilute injections. So the concentration of the probes that I'm injecting are influencing the energy that I am measuring. And this is changing sample to sample. So here we can see that our as received sample has a dispersive surface energy of its highest energy sites of around 105 millijoules per meter squared. Its more average surface energy would be closer to 90 millijoules per meter squared. So we can see that there is a difference between this highest energy site and this lowest energy site. And that is what makes this surface heterogeneous. Now we can see that the annealing process has somewhat relaxed. It has lowered the dispersive surface energy of my carbon nanotubes. And it has also made it more homogeneous. So not only has it lowered the surface energy altogether, but it's made the difference between the highest energy site and the lowest energy site much more small. It's a much more narrow surface energy distribution. And we can see the opposite effect is happening with our sample that has been oxidized. So the introduction to those oxygen groups, the introduction to those electron-rich groups has greatly increased my dispersive surface energy of my sample. So the overall activity of these carbon nanotubes has increased, our dispersive surface energy is higher, and it has made it much more heterogeneous. So it has activated the highest energy sites to a greater degree than it has activated the lowest energy sites. So this distribution overall has drifted to the right, and the highest energy sites have a greater disparity from our other carbon nanotubes. Now here we were specifically looking at dispersive surface energy. So just the energy that was calculated using my non-polar probes, using hexane, using dikane. Now on this next graph, we are looking at the specific surface energy. So how polar is my surface? And we can see a similar trend being observed. So the oxidized sample, this now has that much higher specific surface energy. The introduction of those high polar groups, those high electron density groups, have made it much more polar on its surface and increased the elution times that my polar probes would have had as they were passing through my column and passing over my sample. And we can see the annealing has had the opposite effect. It has reduced the specific surface energy. So perhaps we have removed some polar impurities on that surface. Perhaps we've removed some of those oxygen-rich groups which were causing some of that polarity on the surface. So this has had a very measurable impact on not only how my polar probes are interacting, but also my non-polar probes. And I have a profile and heterogeneity associated with all different energy types. And here we can see the polarity or the wettability that has been calculated for each of these samples. Now, polarity or wettability is just a ratio between my acid and base surface energy and my total surface energy. So it's asking the question, what is contributing more to my energy? Is it my dispersive or is it my specific? And this is accounting for. This is the ratio of what is that contribution. And we can see, no surprise, that our oxidized is, of course, the most polar of the samples. So my next case study, I'd like to look at a very different type of material, and now looking at fuel cell membranes. So we have some different fuel cell membranes. We have a Nafion one, and we have a very different one to compare to also. My apologies. So here we can see the different materials that we'd like to look at. And we were looking at not only the dispersive surface energy, but the specific surface energy. And here we can see the probes that we used. So we packed a certain amount of these membranes into our column. We put this column at 30 degrees C throughout the experiment. We did a number of controlled injection of our probes. And then what we wanted to do was see how humidity would influence the energies that we measure. And here we can see the results of these studies. So here we're looking at the dispersive surface energy, how these materials react. So we can see for our membrane BPSH30, we can see as the more humidity we're introducing to these membranes, the lower the dispersive surface energy is. So we can really see that this is the activity of these membranes can be really highly affected by the humidity that we are introducing. Conversely, we can see that the Nafion membrane is now having a much different interaction than we were seeing before. So we can see that it somewhat stabilizes its dispersive surface energy when we get to 50 and 90% relative humidity. So if you were screening the two membranes as to how they would look in a water fuel cell membrane, you can see that Nafion not only has the higher dispersive surface energy, but is less likely to change that energy as a function of humidity. So here we can see the influence that humidity has on the specific surface energy. And we can see that this is now very different overall. So we can see that as we are increasing our humidity, we are getting the specific surface energy increasing. And that is because we're getting more polar groups on the surface of our material. And that is in helping those polar probes as we're passing it over our sample, that is helping them to slow down. It's causing them to elute slower. So we're getting those higher energy effects of our sample. And we can see that, quite interestingly, our BPSH 30, this is quite resistant to humidity until it gets to 90% RH, at which point the specific surface energy triples. So we're having a really large increase and an activity step under those more saturated conditions. Whereas our Nafion 1135, this has a more linear relationship with how it relates to relative humidity. Now we can see that its specific surface energy is increasing at somewhat of a steady state as we're introducing that different relative humidity. So for my final case study, we're going to be looking at zeolites and how we can characterize porous materials using inverse gas chromatography. So the adsorbents listed above are all alkyl aromatic, and they're known to be harmful to the environment and to human health. So the absorption of these compounds is a solution to reducing these emissions. So this is really a case study that is looking at something like a zeolite and screening these zeolites for volatile organic capture. So these are all porous inorganic materials, and they're widely used as catalysts, as sensors, as storage materials, and are potentially good at removing these sorts of materials at atmospheric concentrations. So the material that is being investigated in this case study is a deilluminated fascicite, which is a Y group zeolite. And this zeolite is well known for having a high surface area. It's also very good for this sort of case study because it's thermodynamically stable, very resistant to high temperatures, it's hydrophobic, and it is resistant to acids. So it would be very stable under a wide variety of conditions that you find in the real world. So here we can see the dispersive surface energy for this material. And we can see that the dispersive energy is the major component. Therefore, a large contribution to its total surface energy will be that dispersive input rather than its specific. So we can see that that is why it would have a very good interaction with our organic molecules because it has this high dispersive surface energy. We can also see a difference between its heterogeneity. So it is much more homogeneous with regards to its dispersive surface energy. We can see this distribution is now much more narrow when it comes to dispersive surface energy. And that is not the case with our specific surface energy. We can see it's much more heterogeneous. So its specific surface energy varies considerably depending on the concentration of the probes that I introduce. So on this next slide, we can see that we have a couple of adsorption isotherms for orthoxylene on this zeolite at a number of different temperatures. So the equilibrium mole uptake is being measured here as moles per kilogram, and that's seen on the vertical axis, and it's plotted against the partial pressure of O-xylene. And this has been done at a range of different temperatures. And the main reason that this is up here is because we can see that this sorption isotherm really deviates from linearity. And that is suggesting that we are having some inhomogeneity or some heterogeneity with regards to the sorption sites that we see on the zeolite. And that is being consistent with the results that we find with its surface energy. So our surface energy is heterogeneous. And we can see that from its surface energy profile measured in inverse gas chromatography. And that heterogeneity is being reflected in how it's a non-linear uptake of our probe molecules. And on the right here, we can see the sorption coefficients of various different alkyl aromatics as a function of temperature. And this is demonstrating a qualitative difference between sorption affinity. As you can see, we have a greater mole, on the right, we can see that as the molecular mass of our molecules gets larger, then we see the Henry's absorption coefficient get larger and larger as well. So the larger molecules with that larger active surface area, that larger van der Waals area, they are exhibiting the largest dispersive force, and they exhibit the larger uptake, and they exhibit the larger energy of interaction. And here we can see how this material compares with other common zeolites and other common porous materials. And you can see how this changes as a function of temperature, which is all measurable using inverse gas chromatography. Now, all of this last case study that I've done is in reflection with our colleague at Surface Measurement System, Annette Condor, and this is a paper that she published using our instruments and using inverse gas chromatography, and how we can apply this sort of technique in plotting sorption isotherms for a wide variety of aryl hydrocarbons. So I recommend this as a read at the end of this presentation. So just to summarize, this is a very powerful technique, and today we've really spoken about surface area, surface energy, and looking at specific probes to introduce. Some of the areas I haven't been able to pan out today are things like glass transitions and monitoring that as a function of temperature and humidity. We can also do permeability measurements. We can look at films on just one side. We can look at solubility parameters, so the Hansen solubility of parameters of APIs, of polymers, to see what we're more likely to solute into another. So with that, I'd like to thank everyone for listening. Thank you for all the other guest speakers for talking today. Thank you for your time, and let's have a nice afternoon. Thank you.
Thank you very much, Connor, for the very detailed presentation. Please, any questions you have, unmute yourself. We have a question.
Questions tab. Hi guys, there's a question submitted in the questions tab.
So by choosing, oh, sorry.
Go ahead, Natalia.
Yeah, sorry. It is from Simon Scherer. And the question is, by choosing the right probes for dispersive as well for the other energy and for BET measurement, is it important to have a higher retention time or less, or to have a broad distribution of retention times for the quality of my measurement?
Yeah, that's a really good question, and one that an experienced user of inverse gas chromatography is always tackling. So of course, in an experiment, you are looking to do anywhere between 50 to 75 injections of probe. And an ideal experiment, I would say, should finish within about 1 day to 2 days. Now, the longer the retention time, the higher the surface energy. However, those long retention times can lead to very long experiments as well. Now, I would say you don't want one injection to go really over an hour and a half. Otherwise, your experimental times just get too large. So in an ideal world, you would want retention times to be long. You would want a lovely Gaussian curve with a big long tail at the end of it. However, that would be for an unrealistic experiment. So you need to look at an ideal sample amount and an ideal probe, which are going to have retention times that are manageable. So I would say for a porous material, you would need something like 5 milligrams on the lower end of the sample that you can use, just to not have it from having really large retention times with the most active probes. And those most active probes will be things like no-name, dicane, okay, largest, the smallest. And if it's very polar, it will be the most polar of our probes. So ethyl acetate, often another one that goes through longer retention times, along with something like ethanol. So it's a hard question to answer. Depends sample to sample, but you're tackling constantly against nice high energy, large retention times with experiments that are doable within the time frames you desire.
Thank you, Connor. One more question from Mishan. Is it possible to determine different functionality of porous materials with IGC technique?
Yeah, just as I mentioned before, porous materials are very useful in this sort of technique. Often we require very small amounts of them, as I mentioned before, because they are a large surface area material. But because we have the high temperature functionality of the system, we can do our injections at 100, 150, and with the high temperature SEA, we can go up to 300 degrees C. That really enables us to do shorter elution times for even a material that has very high surface area. So porous materials are great for a system like this.
Thank you, Connor. One more question for me. Is it necessary for porous materials to use a high temperature instead of the standard one?
Yes, as I mentioned before, higher temperature is going to be more common for those porous materials just because of their high activity and their high surface area. So yeah, going to temperatures for 300 degrees when looking at a thermally stable light is almost a necessity. So yes, high temperatures really important for using these sort of very active high surface area materials.
Great, thank you. Any more questions? Raise your hand or just put it onto the chat box, please. Do you have any more questions for Paul Iacomi in his presentation regarding the DVS carbon and the breakthrough analyzer? And we will actually send you all the presentations, and the workshop as well has been recorded. And we will send you the recorded version as well. If you have not any more questions, I would like to thank you all for attending our workshop today. I hope you found it quite useful. And again, if you have any more questions, please don't hesitate to send us an email, and we're happy to discuss further. So thank you again, and have a great day.
Thanks, everyone. Thank you.